A single massive marine wind turbine generates enough electrical energy daily to sustain 100,000 people. Public perception treats these monolithic white structures as mere decorative landscape elements operating silently inside remote fields. However, clinical telemetry exposes an advanced kinetic energy recovery network concealing colossally intense thermodynamic configurations within. While the colossally huge rotor blades spin slowly, their distal tips exceed 250 kilometers per hour. This extreme velocity remains completely unnoticeable from the ground due to immense physical distances distorting human perception. Approaching within 100 meters reveals massive shock waves of compressed air displaced with every single rotation cycle. Modern offshore installations stand towering at an absolute elevation of 200 meters above the marine baseline. This monumental structural scale effectively matches the combined physical height of two modern skyscrapers stacked vertically together. The immense sweeping rotor assembly spans an operational diameter exceeding 150 meters across space. For comparison, the wingspan of a standard commercial Boeing 747 aircraft measures 68 meters. Consequently, a single carbon composite turbine blade exceeds the entire physical wingspan of that massive commercial aircraft. These giant structures do not operate like typical household fans by simply pushing ambient atmospheric air masses. Instead, the advanced blade architecture mimics an aeronautical wing engineered specifically to manipulate local fluid dynamics vectors. Each blade possesses an asymmetric cross-section featuring a highly convex upper surface and flatter lower boundaries. Passing atmospheric wind accelerates rapidly over the curved upper surface, creating a localized zone low barometric pressure. This calculated pressure differential generates massive aerodynamic lift forces that exert perpendicular thrust against the rotor assembly. This continuous aerodynamic lift force drives the massive mechanical rotation rather than direct brute force wind pressure. This advanced physics principle allows the multi-ton rotor to spin efficiently, even during relatively weak wind currents. The structural materials consist of advanced fiberglass or high tensile carbon fiber layers engineered for extreme environments. These lightweight composites endure immense structural loads comparable to the primary load-bearing elements of massive bridges. Depending on the physical dimensions, a single finished monolithic blade weighs between 20 and 50 metric tons. Fabrication requires several weeks inside highly controlled industrial facilities using specialized geometric molds layered with fabric. Technicians saturate the layers with specialized resin before thermal curing inside massive industrial ovens seals the structure. The final component is a pristine monolithic structure completely lacking internal mechanical joints or structural connection seams. This absolute structural integrity guarantees the blade will not fracture when subjected to colossally intense bending loads. Transporting these gigantic 80-meter components across public infrastructure presents a highly complex logistical engineering challenge. The vertical tower consists of multiple modular steel cylinders measuring up to 30 meters in individual length. Specialized multi-axle transport platforms navigate pre-surveyed routes to avoid weak bridges and insufficient turning radiuses. Moving these 80-meter blades occurs strictly at night when public traffic density drops to absolute minimum levels. For offshore marine environments, installation requires massive specialized construction vessels equipped with 100-meter high cranes. Erecting a single marine turbine requires approximately 3 days provided local meteorological conditions remain completely favorable. Bolted securely to the tower apex sits the nacelle, an armored machine room weighing several hundred tons. A single alignment deviation at an elevation of 150 meters aborts the entire process. This sleek aerodynamic white housing measures 20 meters in length and mimics a massive commercial cargo trailer. The interior compartment features integrated lighting, specialized maintenance tools, and operational space for a technical flight crew. Within this high-altitude laboratory, the slow mechanical rotor rotation transforms directly into high-voltage electrical current. The primary engineering challenge stems from the rotor turning at a slow 5 to 15 revolutions per minute. This slow rotation velocity mirrors the minute hand of a clock, spinning slightly above standard baseline parameters. However, the internal electromagnetic generator demands rotational velocities between 1,000 and 1,500 revolutions per minute. To multiply this input speed by a factor of 100, engineers integrate a massive mechanical gearbox system. This heavy transmission housing utilizes a sequential series of varying gear diameters to accelerate secondary shaft velocity. This industrial gearbox unit weighs 80 tons, occupies significant internal volume, and costs millions of commercial euros. Statistical telemetry indicates this specific mechanical component suffers the highest failure rates over the life cycle of turbines. The accelerated rotational kinetic energy couples directly into a massive generator to induce clean electrical power yields. Intense magnetic arrays rotate rapidly inside copper stator windings, applying fundamental principles discovered by scientist Michael Faraday. This basic electromagnetic induction law, established nearly 200 years ago, underlies every modern power plant globally. Generated current travels down internal heavy cables toward a base transformer that steps up the transmission voltage. High voltage output minimizes resistive thermal power losses as electrical energy transits long distances toward urban grids. Certain next-generation architectures eliminate the mechanical gearbox entirely, using an enlarged direct-drive low-speed generator. This design deletes the least reliable component, but significantly increases the total weight and mass of generators. Mechanical friction and electrical resistance generate massive thermal dissipation loads inside the gearbox and copper stator systems. Industrial radiator loops actively circulate cooling oil engineered to withstand extreme environment temperatures of -40 degrees. No mechanical design survives long-term without adapting dynamically to highly volatile shifting ambient atmospheric wind conditions. Shifting wind directions, varying velocities, and violent hurricane storms present severe physical destruction threats to static tower structures. Consequently, each modern installation relies on an automated control computer that operates continuously without any human intervention. The primary task requires rotating the massive multi-ton nacelle around its vertical axis for perfect alignment. Meteorological sensors mounted atop the housing sample incoming wind vectors multiple times per second for direction changes. When wind directions shift by a few degrees, electric yaw motors actuate to reorient the entire superstructure. This mechanical yaw rotation executes slowly over several minutes to prevent structural twist and gyroscopic stress anomalies. Over an annual operational cycle, the rotating housing may execute multiple complete revolutions around the stationary tower. The secondary automated task modulates the precise longitudinal pitch angle of attack for each individual composite blade. Rotating the blade along its longitudinal axis alters the aerodynamic surface area exposed directly to incoming airflows. Turning the flat surface perpendicular to wind currents maximizes torque, but subjects the structure to extreme load. During weak wind conditions, the automated system maximizes the angle of attack to capture minimal kinetic energy. When winds intensify, the pitch angle reduces to govern rotor revolutions and prevent critical mechanical transmission overload. When wind velocities cross the emergency threshold of 25 meters per second, the system executes radical protocol. The blades turn perfectly parallel to the airflow, eliminating aerodynamic lift and halting rotor rotation within seconds. The turbine enters a passive standby mode engineered to withstand lateral wind forces matching Category 5 hurricanes. Once storm conditions subside below the safety threshold, the industrial computer automatically restarts rotation to resume production. This continuous automation relies on an industrial computer gathering real-time data from dozens of internal sensors. Coded parameters track shaft vibrations, bearing temperatures, wind vectors, blade loads, and exact megawatt electrical output metrics. If any telemetry variable exceeds strict safety margins, the system automatically initiates safety shutdowns and alerts command. Technical teams monitor entire wind farm installations remotely via curved widescreen console arrays matching modern air control. Physical site visits are restricted to scheduled preventive maintenance cycles or critical high-altitude heavy equipment repairs. A modern farm comprising 100 turbines requires a lean workforce of merely a few dozen specialized personnel. Conversely, a traditional coal-fired plant of identical capacity demands hundreds of full-time on-site operational employees. Predictive algorithms analyze internal sensor vibrations to forecast when specific high-load mechanical bearings require immediate replacement. Telemetry models determine exactly when gear oil changes are required or identify microscopic fiber delamination via drones. Automated drones fly precise pre-programmed patterns capturing high-resolution imagery of external blade surfaces to detect cracks. Early detection allows technicians to inject specialized composite compounds on site without dismantling the heavy blade structure. Neglecting a minor microcrack risks the complete structural disintegration of up to 50 tons of expensive material. The total procurement and installation cost for a single offshore turbine ranges between 5 and 8 million euros. However, the operational fuel costs remain absolute zero because atmospheric wind vectors are entirely free and infinitely renewable. This zero cost factor has reduced offshore wind electricity generation expenses by over 2/3 within 10 years. The most powerful serial turbine operating globally is the advanced Danish-manufactured Vestas Model 236. This engineering titan achieves an independent maximum capacity output rating of 15 megawatts under optimal aerodynamic conditions. The sweeping rotor diameter spans 236 meters, exceeding the combined length of 2 football fields. Annually, this single installation yields approximately 80 million kilowatt-hours of high-voltage, clean electrical energy resources. For scale, an average family of 3 consumes approximately 3,500 kilowatt-hours over 12 months. Consequently, a single Vestas unit sustains the electrical needs of approximately 23,000 modern residential families. Factoring in heavy industrial and commercial network consumption, this single asset powers up to 100,000 people. However, electrical engineers must calculate a critical variable known as the capacity utilization coefficient of installed power. These massive wind structures achieve maximum generation capacity strictly when optimal wind velocities interact with the blades. Real-world atmospheric conditions are highly intermittent, with winds dropping below baseline parameters or exceeding safety limits. On average, onshore turbines operate at a utilization coefficient between 35 and 45%. Offshore marine installations achieve higher efficiency ratings up to 50% due to stable high-velocity oceanic winds. Conversely, baseline nuclear generation facilities operate at an unyielding capacity factor hovering near 90% continuously. Traditional coal-fired installations achieve average capacity factors between 75 and 85% of capacity. This variance does not invalidate renewable wind technology, but dictates completely different operational paradigms for modern grid management. A marine array of 100 units theoretically matches a 700-megawatt traditional coal-fired facility. Yet coal plants supply electricity precisely when requested, whereas wind farms produce power strictly when atmospheric gradients allow. This fundamental intermittency underpins the global energy debate regarding whether wind can fully replace traditional power plants. The estimated operational lifespan of a modern industrial wind turbine ranges between 25 and 30 years. Denmark currently leads global metrics, occasionally generating over 100% of its total domestic electricity from wind. Excess energy yields transit across international high-voltage submarine cables to neighboring grids in Germany, Norway, and Sweden. On an annual basis, wind energy represents over 55% of the entire Danish national electricity mix. This achievement stands as the highest integration coefficient for a major synchronized power network globally right now. By the end of 2024, Germany deployed over 70 gigawatts of total installed capacity. Under favorable weather conditions, these wind assets supply over half of the entire nation's electrical power requirements. The German grid architecture handles wind drops by rapidly activating quick-start natural gas thermal generation units. Conversely, during peak wind generation periods, excess power exports directly across the unified European high-tension transmission grid. China currently constructs renewable wind generation infrastructure faster than any other independent nation across the entire planet. During 2023, China commissioned more wind capacity than the rest of the world combined. Total global wind capacity crossed the historic threshold of 1,000 gigawatts by 2024. Despite these monumental metrics, intermittent wind patterns present two severe systemic integration dilemmas for modern electrical grid engineers. The primary threat materializes when atmospheric pressure gradients collapse completely, leaving zero wind across entire continents for days. European grid operators designate these hazardous winter conditions as dark, calm weeks featuring minimal solar and wind outputs. The secondary dilemma involves managing massive generation surges when violent winds produce power far exceeding immediate consumer demand. Resolving both extreme anomalies demands high-capacity grid energy, storage systems, and highly flexible smart transmission networks. Currently, the dominant macro-scale storage method relies on gravitational potential energy inside pumped storage hydroelectric installations. This hydraulic buffering strategy operates heavily in mountainous Norway, acting as a massive battery for regional power grids. Pumped hydro facilities utilize two interconnected water reservoirs constructed at completely different physical elevations across mountain topographies. When excess wind generation surges, grid power drives industrial hydraulic pumps elevating water to the high-altitude reservoir. When wind velocities drop grid, dispatchers release the stored water downward through heavy high-pressure hydraulic power turbines. This gravity-driven fluid motion converts kinetic energy back into electricity, responding to network frequency drops within seconds. This mechanical process is fully reversible, repeating hundreds of thousands of cycles without causing critical equipment material degradation. The steep mountainous fjords of Norway provide the absolute ideal geographic topography for executing this grand-scale storage mechanism. When Denmark experiences wind generation surpluses, power transits under ocean cables to drive the Norwegian hydraulic pump infrastructure. Conversely, when wind currents calm completely, Norwegian hydroelectric assets discharge water, returning stabilizing current across the secret archives. The secondary vector for long-term seasonal grid storage involves industrial-scale hydrogen production via water electrolysis systems. Excess wind current operates chemical electrolyzers, splitting water molecules into pure oxygen and high-energy density hydrogen gas. This clean chemical fuel undergoes secure compression inside massive geological caverns before utilization inside industrial fuel cell blocks. While this chemical extraction process remains commercially expensive, production costs drop rapidly as global infrastructure investments scale up. The third operational storage vector utilizes high-capacity electrochemical lithium-ion battery arrays deployed at strategic grid junctions. In Australia, a massive 300-megawatt utility battery installation connects directly to the high-voltage transmission grid. This chemical array injects stabilizing power into the network within millisecond intervals, preventing widespread cascading blackout events entirely. Isolated wind turbine assets cannot guarantee unyielding national power supplies without these comprehensive backup storage systems operating continuously. This limitation does not stem from weak generator output, but from the historical scale deficits of current storage infrastructure. Consequently, global energy sector capital investments shift aggressively toward expanding these massive electrochemical and hydraulic storage facilities worldwide. The International Energy Agency forecasts total global wind generation capacity will triple by the year 2035. Concurrently, the procurement cost of utility-scale battery storage has plunged ninefold over the last 10 years alone. This rapid economic deflation transforms the majestic white towers from simple landscape elements into primary drivers of global electrification. This technical breakdown from the secret archives confirms that every single blade conceals decades of advanced aerodynamic calculations. Sync your feed with the secret archives to preserve access to these restricted industrial engineering intelligence files immediately. The data vectors inside this segment of the secret archives remain locked for educational and investigative grid auditing.